Hi guys, this is a calculus video, 7-5 for Tuesday, February 28th. There'll be no homework to go along with it, but I'm going to do this video in two parts because otherwise it's going to be super long. So you should watch really two videos to complete this full section of the lesson. Okay, so graphing the solutions to differential equations. And alrighty. So this is part one, and given the graph of the function below, sketch one of its antiderivatives in the space to the right. So you're going to need right now a pen and a pencil. All right, so in pen, let's draw an XY axis. Okay, so in pen. And then in pencil, we're going to sketch the graph, or we're going to sketch a graph of a possible antiderivative here. Okay, so this is f prime. So to graph a possible graph of f, we have to observe where f prime is 0, negative, and positive. Okay, so right here, f prime is 0. I'm not using pencil yet, so I'm going to mark this up with pen. To the left of -4, f prime is negative. Negative to the right of it, it's positive. So what does this tell us about f? It tells us that to the left of -4, f is decreasing because f prime is negative, and to the right of -4, f is increasing because f prime is positive. So on this here, actually, I'm still working with pen. Okay, so still pen for a moment, but I'll just put -4. Now pencil. Okay, so now I'm using a pencil. And I know that f is decreasing to the left and increasing to the right. So like I'll put I can have a relative max somewhere above or below -4. And the graph would look like this. Okay, so I drew that in pencil. All right, so that's a possible, that's a graph of one of the antiderivatives of this right here, f prime. So now we're going to move to this bottom left corner, and we're going to write the equation of f prime. So this is f prime. It's a line, and on this line, we know 2 points. We know 0, 3 is a point on this line, and we know -4, 0 is another point. And to write the equation of a line, all you need is the slope and 1 point on it, and then you can use the point-slope formula. So I know that the slope is rise over run 3/4. And if you don't know how I got that, stop and think about it. So I just did rise over run from this point to that point, or delta y over delta x. And then I could use the point slope formula. So y minus, you could use either point. I guess I'll use this point down here. So I'll do y minus 0 equals m x minus -4. So I'd get x plus 4. So we get that y is equal to 3/4 x plus 3. So this is what f prime of x is. Okay, so right here. So this is the equation of this graph right there. Okay, so there's f prime. Now find the now we're going to move over here. Find the antiderivative of f prime. And then after we do that, we're going to sketch more possible graphs of f, this up here. Right now we graphed one possible f. And then we're going to sketch more possible graphs of f on the graph above. So this is f prime. So to find f of x, I just do the antiderivative here. All right, so I add 1 to the exponent and then divide by it. So we end up with 3/8 x squared plus 3x plus c. But now, guys, remember, when you find an antiderivative, unless you're given an initial condition or a condition that the antiderivative would have to satisfy, like a certain point being on it, unless you're given a certain point that has to be on the graph of the antiderivative, this c could be any constant, any one, all right? And depending on what c is, this graph would move up or down, all right? So we know, guys, that all of the turning points, all of the relative maximums or relative minimums of our antiderivative are all going to have an x-coordinate of -4. But depending on what c is, like c could be 100, and then this relative min would move like way up there. Or it could be like -10, and then it would move way down there. So what we're going to do now is graph a bunch of different ones. Now, what all of these graphs have in common, though, is they all have the same derivative, all right? And what is another name for derivative? Instantaneous rate of change. What's another name? Slope of the tangent line. So they all have the same slope. So really the word parallel applies to lines, but I'm going to use the word parallel here. So when I'm graphing another antiderivative, I'm going to make it so that the slope at every x-coordinate is the same as the slope of that. So see how I made them like parallel. All right, and then I'll do this one over here. And let's do another one. Okay, and then I'll do one right down here. I'll do 2 more. Okay, guys. All right, so there's that. Now, what we're going to do is we're going to graph what's called a slope field. All right, so still with pencil, I'd like you guys to go like this. Let's do a bunch of vertical lines, and these vertical lines just represent like the vertical line will go through a bunch of points, all that have the same x-coordinate. So I did like a vertical line there. Let's do 2 to the left of this, 2 vertical lines to the left of the one in the middle, and then 2 to the right. Oh, we could actually just use that. We could use that, the axis. Okay, and now what I'm going to do, I'm going to draw a little slope. What I'm doing right now, guys, I'll let you know, I'm going to construct something called a slope field, okay? And what we're going to do is, going down this vertical line, all of the slopes here should be the same, okay? The slopes of the tangent lines should all be the same for this x-coordinate that I'm going through. So I'm going to take, now I'm using pen, okay? So, or actually go like this. Still with pencil, draw a point where each vertical line is intersecting these graphs. Okay, with pencil. Okay, and I'm going to construct a slope field by, so now I'm using pen. So using pen again, so we're going to use pen from now on. I'm going to turn my paper a little bit. I'm going to line it up so that my ruler is tangent to the graph at like this point. We'll start up here. And I'm going to draw a little tangent line, okay? And what this little tangent line does is it represents the slope at that point there. It represents the slope of the graph at that point there. And since all of these x-coordinates, since at this x-coordinate, all of these graphs have the same slope, I can just kind of like, without tilting my ruler, without changing the slope of my ruler, I can move it down to the next one. And it should still look like tangent to the graph. A little bit not, but okay. Sorry, I didn't do a great, they all should be parallel, so it doesn't look that great. Okay, now I'm going to move on to the next vertical line and do the same exact thing. All right, so each of these little lines represents the slope. And they all should be like the same slope, but I drew my graph hand, so it's not looking that way. Whoopsie. Yeah, it looks pretty bad. If I drew it perfectly, they'd all be... See, that doesn't look tangent, but it really should be. Okay, now all of these ones... This is where the relative minimums are happening. So it makes sense that the slopes there would be 0. Okay, and now these slopes will be increasing. So I'm just turning my paper like this. Yeah, and if I had drawn the parabolas more carefully, I wouldn't have to adjust my, while going down a vertical line, I wouldn't have to adjust my ruler at all. Like tilt it, adjust its slope at all. They would all be the same. But alas. Okay, so there's that. Now, the reason why we did everything but the little lines in pencil is because now you're going to erase everything. Okay, so now let's erase everything. Okay. Alrighty, and once you have erased everything, guys, you have this thing, this weird looking thing that is called a slope field. Alright, so let's write ourselves a little note. After erasing pencil, what is left is called a slope field. Okay, all right, so that's what's called a slope field. Now, really, guys, this was just an introduction to slope fields. But now we're going, so the way that we're going to use slope fields is not like what we just did. Okay, so in part 2 of this same, like, lesson, then you'll see more how you'll be asked to use slope fields in the future. But this is what a slope field is, okay? You pick a point, like I pick the point 1, I pick the point 0, 1, for example, like pretend that's 0, 1, and this little line segment gives me the slope of this little line segment is the slope of the, is the slope of this, it's the slope of the antiderivative at that point. Okay, I should probably talk less, it'd be less confusing that way. All right, now let's sketch a slope field. Alrighty. So on the blank graph to the right, draw a short line segment at each point representing the slope value. For example, at x equals 0, you would have a vertical set of horizontal line segments. Once you have drawn your slope field, compare it to the graph below the blank grid. Okay, I think I took this from something. All right, so we won't even do that part. Okay, guys, now this is kind of tedious, so definitely speed this up if you want to. But, so this is a differential equation right here. Okay, so differential equation, because it's an equation involving a derivative. And y prime equals 2x. So y prime, the slope depends completely on x. Like there's not x's and y's mixed together. So at the point -2, -2, the slope is -4. At the point -2, -1, the slope is -4. So it doesn't really matter what these y coordinates are. For this entire set of x coordinates being -2, no matter what the y coordinate is, the slope that's coming out is always -4. Okay, so we're going to first graph the slopes for x coordinates -2. All right, so the x coordinates here are -2. So we're going to have -2, -2, -2, -1, -2, 0. All right. So right there. And since we're on a grid, so I want my slopes there, my little line segments to have a slope of -4. So I'm just going to line up my ruler. So 1, 2, 3, 4 over 1. So if I line my ruler up like this, right now my ruler has a slope of -4 because I use the grid to count it. And I'll draw a little line segment. And then I'll try not to tilt my ruler and just keep moving down. All right, so right now I'm graphing a slope field. Okay, I'm graphing the slope field that corresponds to this differential equation. Okay, now I can move on to this next group of x-coordinates of -1. And for all of these x-coordinates of -1, we have a slope of -2. All right, so yeah, so that's what we're doing right now, guys, is we're graphing a slope field. And the way you graph a slope field is you, at each point, you just do a little line segment that represents the slope there. And we get the slope, by the way, by plugging the x value into the differential equation. Okay, so this is -2, so down 2, right 1. Okay, so right there, my ruler has a slope of -2. I could probably do a better job with the, I think that's good. Okay, so there's -2. Now for the set of points with the x-coordinate 0, the slope is 0. Or if we plug 0 into the differential equation, out comes y prime equals 0. And they're all here. So we'll have horizontal lines there. Whoopsie. And guys, really go ahead of me if you've got this. Or speed the video up. Okay. And then x-coordinates of 1. Okay, when x is 1, y prime is 2. So +2 will be the slope here. Alrighty, and then an x-coordinate of, that was an x-coordinate of 1, now an x-coordinate of 2. When x is 2, y prime is +4. And I'm trying to keep so my ruler has the same slope. Okay, guys, so that is a slope field. All right, so we have graphed the slope field. And now I just want to show you something. All right, so if you follow a slope path, you will get the graph of one solution to the differential equation that was used to generate the slope field, okay? Now we're almost done with this part of the video, guys. This is the differential equation that was used to generate the slope field. Okay, so dy dx is 2x. All right, that was, I just changed from prime to Leibniz notation. Now let me try to follow a slope path. All right. So like I'll try to follow this slope path. So if I follow this, if I take a look at this little slope here, and I imagine following it it looks like this one, if I follow this slope, it kind of blends into that one, and then it would come out here. So this takes some getting used to, and I'm not great at it, but it looks like if I follow that slope path, I would get a parabola. It looks like if I follow this slope path below it, it looks like I'd get a bunch of parabolas if I followed the slope paths. And notice this, if you solve this differential equation by first separating the variables and then taking the antiderivative, you'd get y equals x squared plus c, where c could be any number. So this is the differential equation that generated the slope field. This is the solution. This is the solution set. Solution set to the differential equation. And if you take any member of this solution set, okay, so for every different c, there's a different solution set. If you take any member of this solution set, you would get a parabola. So if you follow the slope path of the slope field, if you follow a slope path for the slope field that was generated by the differential equation, you will end up seeing the graphs of the solution set. Okay, guys, so there's that. Wow, very long videos here, so I apologize for that. I hope you're watching on a computer so you can speed it up. Now, take a little break, but there is a second part to this video lesson, so I'm going to make that one right now. Okay, I'll see you soon. Bye-bye.